Okay, so let's look at how we scale or really consider the values of these pumps we're considering, right? So I have 1.2, right? So these sort of separating what the pump did. It's a black box for all we know, but right from 1 to 2, you can still write the head equation. There's always too many terms. Okay. G. One. This is going to be equal to. I don't have time to do a downward equal. Sorry. .2, and then losses. Pump. Okay. From 1 to 2, you get all these things, right? So for comparing your pump design and parameters, we have to non-dimensionalize this expression by something. Now, I want everyone to realize that these don't. These don't refer to the pump that well. These are just end states of 1 and 2. But this losses, clear, right? These losses are definitely part of the pump, right? These losses, if you thought about like some internal flow problem, this is referring to the geometry occurring in the pump. So comparing them, right? This is my actual, right? This is the HA. This is the HA you're trying to predict. So, right, non-dimensionalize this by this. I would be able to judge, right, around where I'm going to have to be. Clearly, I have to overcome the losses. That's what the pump's going to do. But this is definitely a good judge. Right? Likewise, the same arguments actually go for if you think about just the velocity at the outset. So these don't matter, right? Comparing this. So then I'm going to divide everything by this loss term. Right? So remember that losses, what do they look like? They really look like some K value, right? Not beyond minor, right? There's a Q total. You can even write it as a velocity or a flow rate, but just keep it right. If you just looked at all the expressions we had, it was some term multiplying a velocity squared into 2g. And remember that this is some average. So there you go. That's your non-dimensionalization then. So then you can have. Remember, I use these stars for non-dimensional quantities. A lot of people forget to do that. It helps me just remember. Okay, so that would be then the actual pump rise divided by these losses. So velocity can be written as what? That can be written as angular velocity times the diameter squared. Because omega is units of radians per second. A radian doesn't have a unit; it's just units of pi, so it's really 1 over seconds, and diameter is meters, so that's a velocity. So if I want a velocity, characteristic velocity of the pump, right? This is it, right? Makes sense too, because you get it, right? Because if you do like the U, for instance, this is one of the larger radii that you have, but in the scale sense, it is just this, right? A characteristic one of this would be the omega and the d. So then dividing that, you'll have keep the g. Sort of these don't really matter in the scale sense, the k and the 2. Keep the g around because it refers to what planet you're on. Right? So that's non-dimensional head rise. HAG squared. Wonderful. So move along, right? What was the other thing we were caring about? It's this. What values is this going to take on for the pump that I have. Remember, if we go back to the first lecture, we had that Euler equation, or Euler's pump turbomachinery equation, that had the simplest picture we could define. It was just purely, right, it was the most ideal case, but in that we had to, right, we derived some expression for this, right, and it was, and then I had a R, and then it's a theta 1, like that. Okay, assumptions you had was this was 0, the no swirl assumption. But if I were to think about a scale case, remember, scaling doesn't care about negatives and things. So both of these radii, right, scale like the diameter. Their values are kind of around where the diameter is. And these are, this one's 0, but these are kind of around some swirl velocity. Okay, so what do you get if you do that? You get, this is going to scale like rho, omega, and then I have an R2 that turns into a diameter, and then I have some reference velocity that again is, right, some scale velocity. Okay, so more. Again, any sort of scale velocity, you really want to scale it like an omega and a d. Clearly, there's no actual velocity that's going to be much bigger than that if you think about it, because the d's like, right, d's 2r, the most you could get in that u swirl. But it's clearly a good reference for it. So then put one of those in, and then I would have what value is this going to behave like? Well, it's going to have in a scale sense 5. Okay, so on a scale, right, on a scale sense of values that it may be around for your pump design, so the density, working density of the fluid makes sense because power is really proportional to mass. Then you have how fast you're going, and then its diameter to the 5th relationship power. So it's actually a really cool, quick way to maybe estimate how much, right, how much shaft power your design is going to have with just these two quantities of design. So then, like, boom, we have actually our non-dimensional shaft power. I use star for non-dimensional quantities, right? So that is just sort of actual, and we normalize it then by a rho. Okay, that is the non-dimensional shaft power. It's what it is, and you normalize by this value right here. You normalize it by that because of that arguments of scale we just went over. Okay. And then what? Well, you had the power, right? You had, right, shaft, right, and what you had for efficiency is really the other curve. And would I have something else I want to go over? No, that's good. Those are good dependent ones as well. Right, the efficiency. This curve is non-dimensional, right? It's just going to be divided by. It's already non-dimensional. So you could plug this into there to see, right, you can rationalize. Should this be the non-dimensional one or should this be the dimensional one? It has to be dimensional because this is dimensional. Okay. Now let's go over these independent variables of how should we normalize those quantities, okay? So remember, for all lengths, which length should we normalize by? Probably the diameter, right? So then any length will scale with the diameter of the pump, right? So all of these i's scale like the diameter that I have, okay? And this is really motivated by the fact that if you look at this idea of what a pump really looks like, and if you took your measurements all around it, right, in reality, this is going to be the biggest length you've measured, right? The centrifugal diameter of the pump you made, that's the biggest one. This one's certainly smaller than it, right? This one's certainly smaller than it. Even this one is certainly smaller than it as well, right? It goes on and on and on, but if you did the measurements, you would just see that they're all smaller than diameter. So normalization always makes sense to normalize by the largest diameter. Why do you want to do that? Well, if you normalize by the largest scale, let's say if I go from no length, L1, let's say I made an ordering of these, and right from measurement, you figure out that this is the largest one. Dividing all the lengths by it now, this is the important part. You go from 0 now to 1 because I've normalized by the largest length I have. So for all the independent variables that we had, this is how your lengths should scale in there. Normalized by the largest value. So non-dimensionalization, if you just look at the scales, right? For a graph, what you do is, if this is in dimensions, and you have some plot like that in diameter, and let's say a dimensional HA, you're compacting everything down for the non-dimensional case to be bounded on this up from 0 to 1. Everything's happening on the scale of 0 to 1. It's an order 1 plot. That's the point of this normalizing by the largest value, which is the diameter. And all of them are done like that, even the roughness. Right, so those are all of your non-dimensional lengths and how to non-dimensionalize them. How about flow rate? What should the flow rate scale like? So what should the flow rate of the pump order scale like? Well, you wouldn't believe this really works. Okay? Just look at units you could think of, but like the bulkest estimation you could have, the most diameter, right, the most volume this could have, right, is, right, the cube that is the diameter, or proportional to it, right, divided by the seconds, right, so the angular velocity. So it scales, right, as a volume per unit time. So I don't think it's unreasonable to think, well, this would scale then like, it's like this, an omega times d to the d cubed. This is a volume. D cubed is a unit volume. It's like, imagine if you just imagined your pump as like a pure cube. Imagine if it was a sphere, right? It's clearly not, but on the scale, like, it's definitely a good estimate. And then on this omega, because it's units of 1 over time, you multiply omega by d3. Certainly a good scale approximation of what your pump's flow rate will look like. And then you have, right, and then you also have like, and Reynolds numbers, right? Because then you're also seeing, well, what's the behavior of like inertia or inertial forces? How do the inertial forces scale to viscous forces? So don't forget, we also consider the Reynolds number. Why do you consider the Reynolds number? Because you're looking at the inertial forces to the viscous forces. But I'll write that in omega and d. It's not that hard. You just go Vd, but then you do your omega times d is the velocity. You get important part about this that's coming into play for your independent variables in your pump design is this is taking in the information of the fluid. Okay, that is critical because it's the only thing we actually have that's measuring those properties. So the Reynolds number is a measurement of the combination of the fluid density and the fluid friction. So that will have an effect on whatever we're going to derive. Right. Given all that, those are now non-dimensional dependent variable equations, right? So the way in pump, right, the way we talk about this in like pump is we have a CH, right? It's a non-dimensional term. It's called the head rise coefficient. That is equal to sort of call them phi, these non-dimensional functions. Li divided by d, right? Because now I'm taking all the independents and looking only at the non-dimensional terms. And then I have a Reynolds here as well. So this is called head rise coefficient. Okay. 3, efficiency. Same input, same non-dimensional inputs. So what do we say here? This is called head rise. Head rise coefficient, or CH. And then you have power coefficient. And this is just good old efficiency. Okay, so now we have these non-dimensional functions, right? Non-dimensional dependent variables given by scales, and then over here we have the dependent variables as well, right? So really, this is just non-dimensional head rise. This is non-dimensional power, and this is non-dimensional. And this is just efficiency. Okay. Next, which one of these matter?